this video, we're going to take a look at running a two-proportion z-test. Now, what a two-proportion z-test is used for is testing for a significant difference in proportion between two independent populations or two groups from a randomized experiment. What's different about a two-proportion z-test rather than maybe a paired sort of a test is that the data that we use is not paired in any way. The two populations or treatment groups are completely independent from one another. Now, just like all of the other statistical tests that we've run, it's still a four-step process where you need to state your parameters and your hypothesis, state the procedure and check your conditions, calculate the p-value in your test statistic, and then interpret those in context. So we're going to be doing those here. There's going to be a little bit of difference in the formulas and the calculations. So let's take a quick look at those. Since we are making a claim about the proportions in our null hypothesis, in our standard deviation, we are using what's known as p-hat combined because we're making the assumption that these two populations have the same proportion. So we're drawing them from the same population or populations that have the same distribution. So our standard deviation is p-hat combined times 1 minus p-hat combined over n1 plus p-hat combined 1 minus p-hat combined over n2. Essentially what we're doing is we are finding, we're looking at p1 minus p2 as a random variable, and since we're combining those, we have to change their standard deviations to variance and then add them. So we square them, add them, and this is what we get. So the test statistic is a z-score, and that's equal to p-hat 1 minus p-hat 2 over that standard deviation. Now usually we would subtract the parameter, but we're assuming that they have the exact same parameter, that it's p1 equals p2. So that would essentially be 0. We'd be subtracting by 0. So let's take a look at a quick example. Let's suppose we're testing whether or not knowing whether a person is getting a real treatment or not, or whether they think they're getting a real treatment, has an effect on what they feel. So let's say that we've got 60 people that have agreed to take this, to participate in a study about energy pills. And so they've randomly allocated 30 people into a group that gets told that they have the energy pill, and 30 people are allocated into a group where they are told nothing at all. And we're going to assume here that they're actually all getting the exact same thing. They're all getting a placebo, but this group thinks they're getting the real treatment, and this group doesn't know whether they're getting a real treatment or not. So if that's all done, then let's say in the group where they were told they got the energy pill, that 20 out of the 30 reported that they felt more energy, and in the group that was told nothing, 14 out of the 30 were reported that they felt more energetic. Now there is a difference between these two because here we have 20 and here we have 14, but a statistical difference is all about whether or not this difference is unlikely to have just been chance. So what we're going to do is we're going to run a two-proportion z-test because this is categorical. They reported whether they felt more energy or not, and these are two independent treatment groups. So that's why we're running a two-prop z-test. So first thing we've got to do is state our parameters and state our hypothesis. So our parameters here are P1 will be the true proportion who feel more energy when they told they got the pill, and P2 will be the true proportion who feel more energy when they were told nothing. Our null hypothesis could take on a couple different forms. The first thing it could be is that we're going to assume that P1 equals P2, that those proportions are exactly the same. This would be equivalent to saying P1 minus P2 is equal to 0. Like if you subtracted that over to the other side, this would be an equivalent way to write that. It doesn't matter which one you choose. Our alternate hypothesis is we want to test whether there is a difference here. We're not told anything about a specific direction here, so we're just going to say that P1 isn't equal to P2, or an equivalent way you could write that, P1 minus P2 is not equal to 0. So we've completed step 1 where we've set what our parameters are, and we've got our null and alternate hypothesis. So we've got to state our procedure. So what we're going to run is a two-prop z-test. Let's go ahead and run that at the alpha 0.05 level. So we have three conditions that need to be met here. We need an SRS, or random allocation. So it's safe to assume that these groups are randomly allocated to their treatments. We need independence. And that really goes along with the random allocation, that the groups have no influence on each other. And the last thing we need is normality. And what we're going to do with our normality check here is we only actually need to make one, because we're assuming that this came from the same distribution. So if we take a look at our totals here, the combined total here is that there were 34 people who felt they had more energy and 26 who didn't. So that's out of a total of 60 people. So we need to check here that n times p hat combined is greater than or equal to 10. And what we have there is our successes were 34 total. So that's greater than or equal to 10. And we also need n times 1 minus p hat combined to be greater than or equal to 10. And we had 26 of those. So that is also met. So all of our three conditions are met to run this 2-prop z-test. And last thing we need to do now is calculate what those are. I would suggest that you do this on your Inspire, and then it tells you all the important things you need to know. Like our test statistic is 1.56. Our p-value is 0.118. We had started with a p hat 1 of 0.667 and a p hat 2 of 0.467. Our N1, I guess, was 30. We can go ahead and report that too. And our N2 is also 30. So we have all of our values that we need, and now we just have to interpret what those are. So since our p-value of 0.118 is greater than our alpha level of 0.05, we fail to reject. So essentially there is not sufficient evidence to suggest that there is a significant difference in energy when told they got the treatment versus when they were told nothing. So this whole process here, just once again, is we looked at our we had our raw data kind of given up here in this table. We stated what our parameters were, null and alternate hypothesis, check our conditions, calculate our test statistic and our p-value, need both of those, reported the other stuff too to get more detail, and then we compared our p-value to an alpha level of 0.05. And since p was greater than 0.05, we failed to reject the null hypothesis, and we did not find significant statistical evidence that there was a difference in the proportion that reported that they felt more energetic.